Hello, grade 12s. This is the extension of redox reactions. We're also extending from galvanic cell. So this is our third lesson from redox to galvanic. And today we're going to be covering electrolytic cell. Now, before this, let us just go over what we have discussed in the previous lessons. We said in electrochemistry, we can find the EMF of the cell, of the battery, by saying that E naught is the standard potential of the reduction minus the standard potential of the oxidation. Remember, reduction and oxidation can be substituted by cathode and anode. So you just check the formula in the formula sheet at the back of your question paper. Now, remember that in this chapter, we regard an anode, we call an anode a reducing agent. And a reducing agent is simply an electrode where oxidation takes place. And we regard a cathode as an oxidizing agent. So remember that here reduction is taking place because of how we remember red cat. A cathode is where reduction takes place, and wherever reduction takes place we have an oxidizing agent. Now let us continue. Both our cells, the galvanic cell and the electrolytic cell, will operate under standard conditions. What are the standard conditions? We have a concentration of 1 mole per decimeter cubed. So our solutions, the electrolytes, should have this concentration of ions, the 1 mole per decimeter cubed, and the pressure will only be applicable if one of the reducing agent or the oxidizing agent is a gas. So if you don't have a gas between reducing or oxidizing agent, don't include this condition. And then we also have a temperature of 25 degrees Celsius. Now let us go over an electrolytic cell and just check what it does. How does it operate, and probably look at some of its properties. So we have a conversion that takes place. So the conversion that takes place here, by the way, let me just mention that if you understand the galvanic cell, most of what is happening under electrolytic is simply the reverse. Just like oxidation is the reverse of reduction, in a similar way, the electrolytic cell is more of a reverse of what happens in the galvanic cell. So now, in the electrolytic cell, we're simply converting energy. We're converting energy from electrical. So we're using electricity. We're using electricity to get to chemical. Okay, so we're using electricity to cause some chemical reactions to happen, and these are reactions that wouldn't happen otherwise. So if we're using electricity to get some reactions to happen, that means we need to have some source of energy. So now an electrolytic cell will have a battery. So that is one of the major differences between a galvanic and an electrolytic. Here we have a battery. Okay, so we are using up our voltage. We are losing our voltage to get the chemical reactions to happen. So the EMF ends up being negative here. It ends up being smaller than 0. So we understand that these values are negative. Because we're using the voltage to cause some chemical reactions to happen, then the EMF ends up being negative. Now let us go back to our formula. For us to get a negative answer, this number here will have to be smaller than this number here. So the reduction or cathode will have to be smaller than the E for anode or oxidation. Now let us come back. We're simply trying to oppose whatever was happening under galvanic. So in an electrolytic cell, this will be our positive electrode. This will be our positive electrode. I've simply changed colors here. So this is our positive electrode. So here we're gonna have a cathode, a cation. Okay, so we have cat ions here, cat ions, and then our cathode will simply have negative ions. it will simply have negative ions. And what do we call the negative ions? N ions. We call them N ions. So we said this reaction would not happen otherwise. That is why we're using the electrical current to get it to happen. So this is not a natural reaction because we are forcing it. So we say that this reaction is non-spontaneous as such. We say that this reaction is a non-spontaneous. We say this is a non-spontaneous reaction. So this is a non-spontaneous reaction taking place. I hope it makes sense. Now, as we continue, now there are different uses of an electrolytic cell. We use an electrolytic cell as electrolysis. So remember, an electrolysis is simply the breaking down of a substance, the decomposition of a substance. We use electrolysis to purify substances, metals, and then we use electrolysis for electroplating. Electroplating is simply when we coat one metal with another metal. Let us go over electrolysis to make sense of it. And electrolysis is simply the decomposition of a substance. So you know that the formation of water is such a simple process, mixing oxygen with hydrogen. It's easy to create water, to produce water, but reversing the process is not as easy as forming water would be. So we use electrolysis, an electrolytic cell, to break them apart. So all these substances can be broken apart by using an electrical current. So now this is how we get that process to happen. So we would need to have an electrolyte, a solution that conducts electricity. So we put our copper chloride, whatever substance that we want to break apart. So in water, what will happen? This substance will decompose to form ions, copper 2 ions, and then the Cl minus ions. So now we need to connect a battery here for these ions to just separate from each other. Okay, so when you connect a battery, we're going to have a positive terminal, as you know, and a negative terminal. So the negative terminal will cause this electrode to be negative, and the positive terminal will cause this electrode to be positive, because this is positive and there is negative. Okay, now using electrostatics, we know that unlike charges will always attract. So that means we have negative ions here. So the negative ions in this electrode will attract the positive ions in the solution. That means the copper ions will now attach on this electrode. What we'll see happening here is that around this electrode, the copper will be forming a layer here. Okay, so the red color is simply the copper ions forming the layer. And it's the copper ions are attaching to this electrode, so they will form a metal layer around this. So can you see that this electrode is gaining mass? This electrode is gaining mass because we're forming a metal layer around. So now we know that this will be undergoing reduction. So now this will be undergoing reduction, and then the positive ions will attract the negative ions. So what we would see happening here is that around this electrode, you're going to see the chlorine gas forming. So you're going to see some bubbles forming around this electrode. So this is chlorine gas attaching itself on the electrode, but on this side we have a metal copper. So let us check what will happen here. So this will happen. So reduction will take place here, and oxidation will take place here. Remember, we said under an electrolytic cell, the anode is positive. So this is our anode because it is positive, and this will be the cathode. This will be the cathode because it's negative. So remember red cat, and remember an ox. So that means oxidation is taking place for chlorine, and then reduction is taking place for copper. Remember, this is copper. The red color represents copper, and then the green color represents chlorine. So now let us write down our half reactions of what is happening here. So reduction is copper. Reduction is gain of electrons. How to represent a gain of electrons in this chapter? We write them on the left hand side. So this will become, for reduction, we said it's copper. So the copper ions are being reduced. The Cu2 plus is being reduced because we're adding 2 electrons. How do we know that we're adding 2 electrons? It's because we're forming a metal copper. So that means this is a neutral copper. So to neutralize these ions, we need to give it 2 electrons. And then we get a copper, which is a solid. We have a solid as a result. So we should add 2 electrons, which will completely neutralize that charge. And then this is a chlorine gas. A chlorine gas is a neutral element again, but it's undergoing oxidation. Oxidation is the loss of electrons. So we represent a loss of electrons by writing them on the left hand side. So how do we write down that equation? So we say 2Cl minus. So we're moving from a Cl minus, and what happened here? We lost electrons. So the loss of electrons is represented by this. So we have a chlorine gas, but we understand that this chlorine gas was separated from its electrons. So from being a chlorine gas, from being this Cl minus to Cl2 in a gaseous form plus 2 electrons. Okay, remember, when you add the electrons, you should make sure that the charge on the side and that side is the same. So when you say 2 minus 2, you get 0. Again, we have a charge here of a negative 2 because of 2 chlorine ions which are negative. So this is neutral plus a negative 2. So we do have a minus 2 charge on either side. So what is the net ionic equation here? So the net ionic equation here is simply the decomposition. It's the decomposition. So what are we decomposing? So we're decomposing here Cu, Cl2. We're decomposing this to what? To a Cu plus a Cl2. Remember, this is a solid and this is a gas, and this was in an aqueous solution. So we can calculate our EMF of the cell. So the EMF of the cell, you'll find these values again. You know that you're going to find these values from the standard potential table. So the cathode is a 0.34 minus a 1.36. We did say that the anode is bigger than the cathode. We want a negative answer. So if you get a positive answer, that means your interpretation of this was initially wrong. So go back and change everything. So the answer here is a negative 1.02 volts. So that is what we have. So we're quickly going to cover electroplating in this lesson. So we said electroplating is simply when we coat a metal with another metal. So what happens is that we want to have assets that look expensive. So a lot of people will buy a gold ring only to discover that underneath the gold ring is a cheap metal, but it is coated with a very expensive metal. So in this situation, we have this ring here, which is a metal, but it's a very cheap metal. So we want to coat this ring with the silver. So we want the silver electrons to be transferred to this. So the electrons should be transferred here, and these electrons should attract the silver ions. So when the silver ions react with these electrons, they will form a metal surface around the ring, which is silver. So now you should connect the battery in this way. And if you don't connect it that way, you're going to do the reverse of what you are trying to achieve. So now you want this to have electrons. So this should be a negative terminal because you want the electrons to come here. So this should be a negative terminal. So now the electrons will be able to move in this direction. So now this will end up being negative. This will end up being positive. So again, this is our anode. This is the anode. And this is the cathode. So what is happening here? The silver is losing electrons. So that is our oxidation. The silver is losing electrons to the ring. So the silver, which was initially a metal, is losing electrons. So now when the electrons move from the silver to there, the ions here will drop into the solution and then they will attract again on the other side. When an electron moves, the ion, which is Ag plus, drops into the solution and then they attract on the ring again. So now this is what is happening under oxidation. But what is happening on the ring? On the ring, we have another silver reduction half reaction taking place because the silver ions are gaining electrons here. The silver ions are gaining electrons. So it's not the nitrate, it's not the metal that is gaining electrons, it is these silver electrons which are gaining those electrons which are being transferred. So now the gain of electrons is always represented on the left hand side. So we're forming a metal layer on the ring. On the ring, we're forming a metal layer. So the silver ions are attaching on that ring, forming a metal layer.